it's my pleasure to introduce Dr. David Brain from the University of California, Berkeley. David is a research physicist in the Space Physics Research Group in the Space Sciences Lab at UC Berkeley. He received his MS and PhD degrees in astrophysical, planetary, and atmospheric sciences from the University of Colorado Boulder, and before that received a bachelor's in physics and mathematics from Rice University. Dave is the author of more than 4 dozen peer-reviewed publications, and a dozen or more of those has been the first author. And in 2006, he was the recipient of the Carl Sagan Early Career Fellowship in Planetary Sciences from NASA. And David is also the principal investigator on an impressive set of grant awards since receipt of his PhD. And he'll be speaking to us today on the atmospheric escape and Aurora on Mars. And Dave, let me turn it over to you.
That's what we'll do. So today I'm going to talk about the magnetic environment of Mars, which is a really unusual and fascinating place for me. And you've heard a little bit about the magnetic field of Mars in a talk in June or July of this year by Rob Lillis. And I'll be talking also about the magnetic field of Mars, but instead what the implications of the magnetic field of Mars are for the atmosphere. So the talk has 3 parts, all of roughly equal length, I hope. First, I'll basically give an overview and introduction to what Mars's magnetic environment is like. What is Mars like in the solar wind? And then I'll talk about a new type of atmospheric escape process for the Martian atmosphere. And new is in quotes because it's not new. So maybe I should have left that out. But it's one of the first observations of an atmospheric process that has long been thought and even known to exist on Mars. And then finally, I'll end with a bang, talking about Aurora on Mars. And I have 3 goals for the talk, by the way. Goal number 1 is to finish on time, and I will make sure that I do that, even if I have to stop speaking mid-sentence. Goal number 2 is to explain to you why I find plasma and magnetic fields at Mars really exciting. And goal number 3 is to convince 1 or 2 of you in the room that I'm right. So let's start. Mars in the solar wind. I'm going to use this thing so I stop blocking the projector. Let's see if it works. Oh, wow, cool. Okay. So it even works that way. Mars in the solar wind. What happens when you bathe an entire planet in a fluid of charged particles coming from the sun? Not only charged particles, but photons too. Well, every solar system body and every body in the universe is essentially being bombarded by plasma and by photons in some form or another. And you can describe all of these plasma interactions by 2 basic characteristics. The first characteristic is, what is the plasma that's doing the interacting? Is it solar wind plasma, or is it some sort of magnetospheric plasma, or something else entirely? And then the second basic characteristic is, what's the nature of the body that's being interacted with? What is the obstacle to this plasma? And Mars is kind of a funny place because it has elements of 3 different types of bodies in our solar system in its interaction. It's very Venus-like because Mars has no global dynamo magnetic field. If you have a compass on the surface of Mars, you are lost because you have no idea which way north is. And that also means that the planet doesn't have a protective shield from solar wind plasma, much like Venus. It's also similar to comets in that Mars is relatively small, and so its atmosphere is very, very extended. And the atmosphere extends even upstream of the bow shock, the plasma bow shock. And so the planetary atmosphere participates significantly in the plasma interaction. And number 3, and this is the exciting and relatively recent new information, is that Mars has strong crustal magnetic fields. And so it does have some elements of an Earth-like or Jupiter-like or Saturn-like or Uranus-like or Neptune-like magnetosphere, in that the planet itself provides some magnetic field that is able to stand off or block the solar wind. So when you put all of these 3 things together and you zip them up and you change them into Mars, you get some relatively incomprehensible looking diagram like this that explains how the plasma interaction works. And basically, they're charged particles, protons and electrons from the sun, going towards Mars, and they're carrying a magnetic field with it. And at some point, these particles have to interact with the planetary obstacle that's there, Mars's atmosphere. And first of all, you can think of the magnetic field lines as big spaghetti noodles. As they get closer to the planet and they start interacting with the planet and they realize that it's there, the spaghetti noodles, just like throwing them at a basketball, wrap around the basketball and drape around. And then they slip up and over and then head on back downstream. And the particles that are protons and electrons that are entrained in the spaghetti noodles also interact, and they interact with atmospheric particles. And first, there's a bow shock, much like a fluid bow shock in a stream or a brook that you'd see. And then there are all sorts of other plasma boundaries downstream that I won't go into in much detail. A magnetic pileup boundary is much like Earth's magnetopause. There's probably an ionosphere at Mars, this boundary between yellow and blue. And when all of this happens, there's all sorts of exciting physics that could happen. And I'll hopefully give you the idea that some of this physics is even important from a planetological perspective. But basically, the particles and magnetic field from the sun interact with the planet, and all sorts of things can happen. And ultimately, atmospheric particles can be stripped away from Mars, much like throwing little pebbles into a swimming pool. Every time you throw a pebble into a swimming pool, you can splash a drop of water out. And if you do that for 4.5 billion years or 4 billion years, maybe that's an important process. And that's something that we're trying to figure out. OK, but Mars also has crustal fields. This is what gets me out of bed in the morning. They're really, really cool. And they were discovered in 1997 by a Mars Global Surveyor spacecraft. And this is an example of one of the Discovery type observations. You see a spacecraft trajectory right here. And superposed on this spacecraft trajectory are real data taken by the magnetometer on the spacecraft in the form of whiskers. Each little whisker tells you the strength of the magnetic field. And here's a scale bar down here of 1,200 nanotesla. And the direction of the whisker tells you the direction of the magnetic field. And as you get closer and closer to the planet, the magnetic field gets larger and larger and starts rotating around and cycling around in very coherent ways. And you can look at this slide, and you can just see that the magnetic signatures are coming from the planet. They're apparent when the spacecraft is close to the planet, but they're not coming from the deep interior. The scale size of these structures is such that most of the signal is actually coming from the outer 40 or 100 kilometers. These are very strongly magnetized rocks, thousands of kilometers long, hundreds of kilometers wide, tens of kilometers deep, and it's the signature of the magnetic fields is 10 to 20 times stronger than the signature of magnetized rocks on Earth from Earth's magnetic anomalies. So in some sense, you could make the claim that this is the most strongly coherent magnetized rock that we know of in the solar system. And it's either strong or coherent, or both. If you fly over the planet for 9 years or 7 years in a mapping orbit, you can start to make maps of what the magnetic field looks like. And you've heard about this in a previous seminar, so I won't go into this in too much detail other than to say the crustal magnetization is mostly remnant of an ancient dynamo at Mars that shut off 4.1 billion years ago or so. And there are very strong crustal magnetic fields in the southern hemisphere. Places where there was high heat flux, such as impact craters or volcanic regions, are largely demagnetized. And the southern hemisphere is more strongly magnetized than the north. The southern hemisphere is older. Rovers, Spirit is around here. Opportunity is over here somewhere. Pathfinder and Viking 1 were up here, and Viking 2 was over here. So many of the rovers and landers that we've had on Mars have been in at least weakly magnetized regions. You can take that map and play with it in a different way. And at 400-kilometer altitudes, you can make a map of what the average magnetic field from the planet looks like, again, in the form of a whisker plot. And now the whiskers are colored by the component of the magnetic field towards the center of the planet or away from the center of the planet. Reds are up magnetic fields, and blues are downs. And you can see a smiley face with 2 eyes and a mouth over there. This one over here is really cool. It's a fountain of ups surrounded on all sides by downward magnetic field. Everywhere ups are connected to downs. So if you look at this long enough, you can see a butterfly right here. There's a ship, and clearly I've been looking at this for too long because I'm starting to see things that are not there. Yes, Kevin. What's that? Hellas, I think right in there. Right in there. Here, let's go back. Here's Hellas. Okay, so there are two consequences of magnetic fields. These were discovered in 1997, and people have been publishing about the consequences ever since, and there's a whole litany of papers about why crustal magnetic fields are or are not important. But all the effects that have been published over the last 12 years boil down to two main effects. That's basically two reasons that crustal fields are important or change things. Number one, they add magnetic pressure. Magnetic fields have pressure of their own. The crustal fields are actually strong enough that they add significant amounts of magnetic pressure that can locally repel or stand off the solar wind and protect pockets of Mars's atmosphere. Okay. Also, crustal fields changed field topology, and I mean the word topology in the mathematical sense here. Where are field lines connected? Are they connected at both ends in the solar wind? Are they connected at both ends to the Martian crust? Or are they connected at one end to the Martian crust and at one end to the solar wind? And you can see green is both ends in the solar wind, blue are open magnetic field lines, and red are closed. Okay, this is sort of theoretical and model calculations. You can get fancy with those and actually make movies of what the magnetic pressure boundary is at Mars. And you can see that Mars is a lumpy and bumpy obstacle to the solar wind. If you were the sun and you had goggles that could view the pressure balance boundary at Mars, where Mars's atmosphere is protected, this is what you would see. It's a little disturbing. Looks like Mars has warts. But they're basically crustal fields protecting pockets of atmosphere in some regions and no crustal fields in other regions, so the ionosphere has to supply all the pressure itself. Okay, if this were Venus, this whole thing would be smooth. The ionosphere would be doing all the work. If this were Earth, the pressure balance boundary would be out here somewhere because Earth has a big global magnetic field. Okay, crustal fields change topology too. You can make nice little animations of where field lines should be closed and open and unconnected. And that makes for a great movie and a nice little visualization. But in both of these cases, you want to know if this picture is supported by data. And it turns out that it is. Okay, we've looked at both of these things, and we've mapped where solar wind is excluded at Mars, and we see that it's excluded above crustal fields. And we've mapped where open and closed magnetic field lines are at Mars, and we can see where closed and open field lines are in a steady state, but also how open and closed field regions change as external conditions change as well. So if I had to say, pardon me? In terms of pressure balance, you can see, let's talk about topology instead. Closed field regions. Actually, I can show you something at the very end, but I'll just tell you now that you can see the closed field regions breathe in and out, up and down as the pressure in the solar wind changes. As pressure increases, closed field regions shrink, even on the night side of the planet. And you can also see these cusps of open magnetic field lines. And if the direction of the magnetic field in the solar wind changes, then those cusps close up. So every time the solar wind field changes, you have regions that are opening and other regions nearby that are closing. It's really kind of exciting to see things zip open and closed. So it's a very, very dynamic environment. But closed field, there are some regions on the night side of Mars in the very strong crustal field regions that at no time in 7 years did we ever observe anything other than a closed field line. So there are some regions that are always closed and protected. Oh, and the last throwaway point I wanted to make is that magnetically speaking, I think Mars is more similar to the sun than any other object in the solar system in terms of its complexity. Why should you study plasma at Mars? Well, I'm going to talk about two examples for the rest of the time here that touch on all three of these reasons to study plasma at Mars in the magnetic environment. One reason that's sort of made perhaps overly much in literature and in proposing is that studying Mars as plasma environment is relevant and important for climate evolution. And the answer is we don't know whether atmospheric escape at Mars has been important for climate evolution. Many people suspect that it has been, but it may turn out that it hasn't been particularly important for climate evolution. But studying the physical processes that occur there and that are stripping away Mars's atmosphere today not only gives us insight into Mars, but into many other bodies in our own solar system, such as comets, or planets around other stars that are hotter and more active. So climate evolution is an important reason to study plasma at Mars. Also, the plasma environment is the upper boundary for the Martian atmosphere. If you want to study the upper layers of the Martian atmosphere, you need to understand that upper boundary. So it's important to study this environment. And finally, it's a great plasma laboratory to study fundamental plasma processes, such as field-aligned potentials and auroral acceleration, magnetic reconnection, things like that. If you want to understand physics, it's always good to test your theories and observe physical processes in another plasma environment. So now let's talk about this new type of atmospheric escape process with new in quotes. And I have a comet in the background here because Mars is basically like a big version of a comet. And if you've ever seen a comet with your naked eye in the night sky, then you've seen atmospheric escape occurring. Okay, this isn't a pie in the sky process. I guess it's a comet in the sky process that we know happens at solar system bodies. And so there are many lines of evidence that suggest that Mars's atmosphere is thinner today than it has been in the past, either permanently or episodically. As a matter of fact, there was something in the news in the last 2 days or so about a big meteorite found on the surface of Mars, and questions about how something that big could have survived to the Martian surface. And so there are all sorts of lines of evidence that suggest that Mars's atmosphere used to be bigger. I'm not sure many people dispute that claim. The question is, when did it used to be bigger, and how much bigger was it than it was today? Regardless, the atmosphere had to go somewhere. And where did it go? Here's the answer. It went 2 places. It went down, and it went up. And we know that both of these things have happened. And so I'm done. Thank you very much. Any questions? So I study the up, basically. What are the processes that contribute to atmospheric escape to space? And this is a particularly attractive process because you know that once something escapes upward, it's not coming back. Okay, things that can go down can always come back, but things that are removed out of the top are probably gone for good. So let's go back to this messy picture, and I'll tell you that there are 3 classes of removal process for neutral particles and 3 classes of process for ions that are believed to remove atmosphere from the planet. And many of these processes have been observed using spacecraft observations. So the 3 for neutral are thermal escape. You just have a bunch of particles that have a temperature. It's an ensemble of particles with a temperature. Some of those particles are going to have a lot more energy than others, and if that energy is high enough, then they have escape energy from the planet. This is really only relevant for hydrogen at Mars. Another neutral process is photochemical escape, where you have some sort of input from the sun, and it creates chemical reactions and provides energy, and then those neutral particles can escape as well. And then a third neutral escape process is sputtering, where you have something splashing off the planet, maybe with not quite enough energy to escape, and it comes bouncing back down in, and when it crashes in, it splashes off other particles. Those are all fun to think about. I don't think about them myself. I think instead about ion processes, and there are 3 ion processes. One is pickup, where you have atmosphere far enough away from the planet that can be ionized either by the solar wind or by sunlight. It sees this big magnetic field in the solar wind that's moving. There's an electric field, and so these ions start to gyrate and are carried away from the planet. This is the process that most people think of when they think about atmospheric escape at Mars, because it's very easy to think about. But there are 2 other processes. One's called ion outflow, and that's where the solar wind doesn't have access. The ions aren't high enough in altitude to be picked up, and so they have enough energy. There's some sort of transport process or energization process down at low altitudes, and they can just flow away, maybe something like auroral acceleration. Finally, there's this process up here called ionosphere escape. It should be bulk ionosphere escape. And this is where you have whole blobs of plasma, not just individual particles, but a whole chunk that gets torn off the ionosphere and loops away downstream. And this is something that people have shown in simulations, have shown theoretically, but it's been very, very difficult to observe this happening at Mars. Okay, if you add up the believed rates for all these escape processes today, you get a rate that really doesn't add up to much planetologically over the history of the solar system. It suggests that atmospheric escape may not have been as important as some people are claiming. But then if you think about how efficient these processes may have been in the past, for example, solar storms were probably more intense and more frequent. The solar wind was stronger, then loss may have been a more important process long ago in Mars's history. So this is one reason that people are still interested in studying this. So bulk escape has been observed at comets directly, and this is kind of a sexy observation. This was from 2007. This is Comet Encke right here. And the sun's over here, and the sun is about to release a CME, coronal mass ejection, basically a solar storm. And we'll watch this CME hit the comet. This was recorded by the Stereo spacecraft, and you can see the comet's tail here. Watch what happens to the tail. Whoa. Okay, and so this is a huge input of energy from the sun into the atmosphere of the comet. It tears whole chunks of the atmosphere right off and bloops away. Okay, and again, Mars is like a big version of a comet in the solar wind. Mars does have gravity. You probably don't expect to see anything as dramatic as this, but you do expect to get ripples in the ionosphere and bloops and things like that. But this is, yeah, admittedly a melodramatic example of bulk escape. Okay, so now I'm going to get plasma-y for a few minutes. This is a time series of magnetic field data from Mars Global Surveyor. About 40 minutes of data. The spacecraft was in darkness and in sunlight, and it was at a constant altitude of 400 kilometers the entire time. Okay, and these are the observations in black. Okay, and this is what a model of crustal magnetic fields only at Mars predicts the spacecraft should have observed. Okay, the difference between model and data on the day side, a roughly constant difference, can be explained by the fact that this red model doesn't include the magnetic field of the solar wind, the draped spaghetti noodles. Okay, if you add those back in on the day side, you can reproduce the data reasonably well. Okay, what is a big exciting mystery is this huge 180 nanotesla thing. Okay, that's a lot of nanoteslas. 180 is on a par with the strongest crustal magnetic field measured at this altitude at Mars. But if you look, the crustal magnetic field model predicts there should not be a crustal magnetic field there at all. And this is a narrow feature in time. It's likely not a transient solar wind feature passing through. So it's kind of a struggle to explain this. It almost looks like a crustal field that's out of place. So let's look at the orbit geometry. And now we're looking at Mars from the bottom, from above the South Pole, with the sun off to the right. And here's the spacecraft in time. Okay, and here's the dark light boundary going this way. And there are crustal magnetic field, big crustal magnetic fields here on the day side. And it observed this odd feature right here. Okay, near the day-night boundary, but more notably downstream from crustal fields, because the solar wind plasma, my thing just, oh, there we go. Solar wind plasma is moving this way past the planet. Okay, so that's a clue right there. And not to keep you in suspense anymore, this is, we think, either a plasmoid or a flux rope, which are two alternate terms for basically the same thing. And the reason we think that is because not only do we have magnetic field magnitude information, we have vectors, which way was the magnetic field pointing. And you can find a coordinate system, you can search around and you can find a coordinate system that tells you that all the variation in the magnetic field was in a plane. Okay, there was very little out-of-plane variation, and the field was just sort of dialing around like this. And actually the field looks a lot like a slinky. Okay, and in 1979 at Venus, very similar signatures were seen in the Venus ionosphere, although with much smaller magnetic field strengths. And this was termed a flux rope. Okay, because it's a rope of magnetic flux, and it actually looks like concentric slinkies. So there's a slinky on the outside, and then a even more stretched slinky interior to that, and interior to that, even more stretched, and when you get to the very center, it's just straight. And so that's what it looks like. And as a matter of fact, our flux rope up here at 180 nanoteslas or so is the strongest flux rope that's ever been measured in the solar system, as far as we know. Okay, so we believe this is a flux rope, and not only do we have magnetic field information, but we have plasma information in the form of electrons. So let's look at this same event again and define a few time periods. 2 time periods before the flux rope, 1 during, and 1 after. Okay, and you can look at the flux of electrons as a function of energy, and you can see during all the periods actually, but during period 3 as well, there's kind of these bumps in the electron energy spectrum. Those bumps are very characteristic of electrons from the Martian ionosphere, which are created by sunlight, ionizing, and these are CO2 photoelectrons down here and oxygen photoelectrons right here. So we know that this flux rope is filled with ionospheric plasma, and it's actually filled with a lot. And I won't go into why it's filled with a lot. Also, you can look at the topology, and you use electrons to tell you whether the field lines are open and closed. And the only thing I'll say here is that as a function of direction, we know which direction all the electrons are coming from. This period 3 doesn't look anything like periods 1 or 2 or 4, where there are a lot of electrons focused in one direction. Okay, the electrons are all mushed and spread around, and places that are immediately adjacent to the flux rope look very different. And so we say that this rope is filled with physically isolated ionospheric plasma. So this is a slinky structure filled with atmosphere with different plasma characteristics on the outside. This, yeah.
So are ultraviolet surveys the same terrain on multiple passes? Do you see that same piece on other passes?
Good question. Ta-da. Sort of, yes. This is not a unique event. I'll say that. Okay. So I looked through 7 years of data, 20,000 orbits or so, and found 21 events that were similar. But I set an artificial threshold of the event had to be 100 nanotesla or more, which is a big, big event. So we found 21 big, big events. This is not unique. Every one of the 20 events, as you fly from the beginning of the event to the end, beginning to end, shows that the event is downstream from these big crustal magnetic fields in the southern hemisphere. They're all blooping off of crustal magnetic fields. So the crustal magnetic fields are some kind of a leaky faucet that's sending all of this downstream.
So when you searched for them, you didn't actually assume that they were downstream.
No.
When you went from the 20,000, you just matched that shit.
Not even that. I said, let's look for any place where the difference between the crustal magnetic field model and the measurements is 100 nanotesla or more. That turned up about 2,000 events, and then by eye, I went through the 2,000 events and matched the shape and found 21. Okay, and 20 of the 21 are downstream from crustal magnetic fields. This is an anomalous event, and it's super, super narrow. It's about 3 times narrower than this feature, and I think it's a passing transient in the solar wind. Yes. And so as a matter of fact, I've now gone back. I haven't done it formally, but I've gone back and just looked at orbit after orbit. And there are flux ropes or plasmoids leaking off crustal fields all the time, almost every orbit. They're rarely this strong. They're usually 10, 20, 30 nanotesla or so. So my initial check didn't have that threshold. And those are much harder to find because they tend to look like crustal magnetic fields. So you have to use your brain when you're trying to find them. And it's long, laborious, boring work, and so I have an undergrad that's going to be doing that this fall. So what is this thing? I mean, we've already talked about it a little bit. It could be a solar wind transient passing through, but it's filled with ionospheric plasma, so I rule that out right away. It's possible you could put ionospheric plasma in there as it's passing through, so you can't rule it out entirely, but that's not it. It's one of these two things. And really, it doesn't matter which one, because either way, it's exciting. It's either a crustal field that's been stretched out like a windsock way behind the planet in a place we don't expect to see crustal magnetic field lines at all. Okay, and if it's stretched out that far, it probably is going to break off and carry plasma away from the planet. Or it's a crustal field that's been stretched out and has already been broken off, and we're observing this flux rope plasmoid carrying away atmosphere downstream. And so it's a direct observation of this bulk escape process. Okay, and so I'm hoping through statistical analysis of these many thousands of smaller flux ropes to figure out if one or the other or both is happening at Mars. Okay, this 3 here, there are 2, if we want to get into the space physics of what's going on and why that's interesting, there are 2 ways to break off plasmoids. One is you just stretch it out so far that you have oppositely directed magnetic field on either side of the rope. Those oppositely directed magnetic fields get close enough to each other to cancel, and you end up with a closed structure over here, and then the original crustal field line back here that snaps back into place. So magnetic reconnection. Another possibility is that you have instabilities in the surface of the crustal field itself that are caused by magnetic shear. These instabilities steepen, like Kelvin-Helmholtz, and eventually pinch off and break off and carry things downstream. So 2 questions. Let's go here, and then Kevin.
Yeah, I was just wondering if you answer the same thing. Do you think these have sufficient energy to escape?
Yes. I think once detached,
As they go through them, if you could repeat the question.
do I think these things have sufficient energy to escape? Yes, I think once detached, then they're going to be caught up in the solar wind, the shocked solar wind flow that is sweeping past Mars all the time, and they'll just be carried away downstream. Kevin? Do these things cause the crustal field to erode?
Power to continue generating the crustal magnetic field as these things take them away. It's kind of obvious to me because there's no magnetic monopole, so it's not like
Right.
an obvious thing.
So do these,
Where is it coming from then in these fluxes? Is it coming from someplace other than the magnetic field?
yes. So there are two questions. Do these things cause the crustal magnetic field to erode? And where does the energy then come from to create these things? And I believe that the answer to the first question is no. The crustal fields are, generated in the subsurface of Mars, in the outer 40 kilometers or so of the crust, and that magnetic field is there. It decays slowly over billions of years just because the magnetized rock has some sort of time constant for decay. And so the energy for creation of these flux ropes must come from the solar wind. And so I can explain, for example, in the Venus case, why people think flux ropes form. It's because you have these spaghetti noodles of magnetic field interacting with the ionosphere. Okay, and here in the center, where Venus is, the spaghetti noodles encounters the ionosphere, but out on the edges, it's still out in the solar wind, so it's sailing past. And so that's what makes the spaghetti noodle magnetic field lines wrap. And the ones that are getting dragged through the ionosphere can sort of twist up. If you hold a jump rope or something like that and drag part of the jump rope through cotton candy, it might start to twist up. And so that energy basically comes from the solar wind flow flowing past the planet and can twist up magnetic field lines. And I think basically the magnetic shear from the solar wind interacting with the crustal fields either in this manner or stretching them out is what provides the energy for them to then break off. And another interesting aspect of magnetic reconnection is it's a huge particle accelerator. It converts magnetic energy into particle energy. So that's interesting for another physical reason, is that it can serve to accelerate particles and provide them with additional energy. All right, I think we're on track time-wise, which frankly amazes me. So here we go for part 3, Aurora on Mars. And before we talk about Aurora on Mars, I want to... Yes. Well, I want to tell you a little bit about this picture. This picture was taken by a guy named Stan Richard. We've only ever spoken by email, in 2003. And he's either from Iowa or Wisconsin, and he either took this picture in Wisconsin or Iowa. He lives very close to the border, and I can never remember which. And this is a nice picture of red aurora on Earth with Mars in the background. So it seems very appropriate. Pretty cool. And so he lets me use this when I talk about Aurora. But he has a nice website, and you can go to his website and buy his pictures if you like. His name again is Stan Richard. Okay. So Aurora in the solar system. Aurora have been observed throughout the solar system, and frankly, it's a little surprising or embarrassing that Mars is only the latest planet to join the party. But that's because nobody was really looking at Mars until recently. So of course we know that aurora happen on Earth. Beautiful, beautiful aurora happen on Jupiter, aurora on Saturn, even aurora on Ganymede, one of the moons of Jupiter, occur. Uranus and Neptune, auroral UV emission has been observed by Voyager, and depending upon how you define aurora, you can argue that they've also been observed on Venus and on Titan. Aurora basically, in my mind, describes a string of physical processes, the very last of which is glowing of the atmosphere as a result of impinging particles. Okay, but for many people, aurora is just the light itself. But basically at Earth, charged particles from the solar wind are trapped in Earth's magnetosphere. They hang out in the magnetosphere for a while. And then something, which is the object of one of the heliospheric missions of NASA, is to figure out which something it is, causes those particles to be accelerated up field lines and come crashing into the atmosphere at the North Pole and South Pole. The crashing in of mostly electrons, but ions too, into the atmosphere excites particles in the upper atmosphere, and when those particles jump back down to a lower energy state, they emit photons in the form of aurora. Okay, many people think that you need to have this focused magnetic field and focused deposition of particles for it to be called aurora, which is why Venus and Titan have asterisks next to them, because they don't have their own magnetic fields. So at Mars, we have 3 observations of auroral processes from 2 spacecraft. And I'm going to talk about 2 of the 3 observations and just skip 1 because of time constraints. And so first, we'll talk about Mars Express, the European Mars Express spacecraft at low altitudes on the night side at about 130 kilometers. And basically, a UV instrument on that spacecraft has observed a spike of light coming from a crustal magnetic field cusp, and they've called it aurora at UV wavelengths. Okay, then Mars Global Surveyor, the spacecraft I was talking about before, with its Electron instrument on the night side, has observed electrons shooting down into the night side atmosphere, and these electrons have characteristics of aurora as observed on Earth. And then finally, Mars Express at higher altitudes. This was at 130 kilometers, this is at 400 kilometers, and this is at 1,000 to 8,000 kilometers. Mars Express with its particle instrument, but no magnetometer, has seen electrons generally rushing back toward the planet at the same time that ions are rushing away, as if there's a large electric field there that is accelerating particles in different directions. So all of these suggest that auroral processes are happening at Mars. So let's talk about the first 2 just briefly. As a function of time, in 2005, I believe, the Mars Express spacecraft was taking UV observations on the night side of the planet, which was a search actually for night glow at Mars, not for aurora. But just by happenstance and luck, they managed to catch this brief spike, very intense flash of light on the night side of the planet as they were going from night to day, where the UV emission and all their energy channels got to be very large. Turns out this spike of light came when it was a limb viewing observation, so it wasn't looking down at the planet, it was kind of looking off to the side in the upper atmosphere, and they were scanning along. And the spike happened right when they were looking through a crustal magnetic field cusp, and then went away. And they actually had 5 different channels, 1, 2, 3, 4, 5. And so by timing when the light increased in each of the 5 channels, they could really triangulate or pinpoint where the light was coming from to within 30 kilometers or so. And it's definitely coming from a crustal magnetic field cusp. And they have spectral information in each of their channels. So by subtracting off the spectra surrounding this auroral signature, they can come up with a spectrum of the light coming just from the aurora. And it's basically a result of excitation of a CO2 atmosphere. Okay, it's Cameron bands, CO Cameron bands, about 2 kilorayleigh, which is weak by terrestrial standards, but nothing to sneeze at. And then 200 Raleighs is probably something to sneeze at, but they see 200 Raleighs in CO2 as well at 289 nanometers. This got everybody all excited. There was a Nature paper and a flurry of research and a flurry of activity. And everybody said, okay, yeah, you saw one. Maybe it was just a meteor passing through the atmosphere that interacted with the atmosphere and caused emission, and you got lucky. So they went back and actually took some more observations at night, almost all in the southern hemisphere. So everywhere you see black is where they tried to find aurora. Everywhere that you see white is where they actually found auroral emission again. They found 8 events out of 21 orbits or so, and almost all near the strong crustal fields. And as a matter of fact, when they look at a map of magnetic field topology, here's a map of topology colored according to the probability of there being closed field lines on the night side of Mars. Every one of their auroral observations is sort of at a boundary of closed magnetic field lines, sort of at the boundary between open and closed. Okay, so it's where these cusps of magnetic field are that they're seeing the light. They're seeing the light. Okay. Sorry. Entertaining myself up here. Okay, let's move on to Mars Global Surveyor. Here's Mars Global Surveyor, and these again are electron energy spectra. Boring, boring, boring. Plasma, plasma, plasma. But I'll tell you 2 reasons that these are exciting. Number 1, this is not a happy electron energy spectrum. Happy electron energy spectra have lots of electrons at low energy, very few electrons at high. They don't have these bumps in the middle. Something has happened to create this bump to make a lot of electrons have one single energy. Electric fields can do that by accelerating electrons. If you have a set potential of maybe a kilovolt or so, you can accelerate a lot of electrons to a kilovolt, no matter what their initial energy. Okay, and this one at 4 kilovolts here accelerated so many electrons that our instrument saturated, and we don't know where the peak of this curve is. Overall, we have 13,000 examples of electron energy spectra that look like this. And when you go and look at Earth data, for example, from the FAST satellite, in Earth's auroral zone, you see electron energy spectra that look very similar. There's one big difference here. Our peak energy is at 4 kilovolts, 4,000 electron volts. Typical auroral energies at Earth are 5 kilovolts to 10 kilovolts or something like that, whereas our most extreme example is in this range. So we're at lower energies, more or less. But we have 13,000 examples from hundreds of orbits or so of auroral-like electrons shooting down into the Martian atmosphere. So here's one auroral event as a function of time, and I'll just go through this briefly. As a function of time over the southern hemisphere, as you're going from north to south, here are 3 components of magnetic field, and here are a bunch of electron energy spectra as a function of time, this time shown in spectrogram form. These are happy electron energy spectra over here. Lots at lower energy, few at high. These are unhappy in here, where you have a bump at some intermediate energy. These are auroral-like electrons here. This red dashed line corresponds to this energy spectrum right here. Black dashed line corresponds to this one. Okay, and you can again look at where the electrons are coming from in pitch angle space. So are the electrons coming along the magnetic field line, anti-parallel to the magnetic field line, or are they just spinning around the magnetic field line at 90 degrees pitch angle? And you can use these pitch angles to tell you that over here, these are open magnetic field lines connected at one end to the crust and at the other end to the solar wind. Here, with a whole bunch of electrons at 90 degree pitch angle, these are closed. And so you can see these auroral electron spectra are on open field lines very close to closed field line regions. And you can look at the magnetic field, and you can see these jumps in the magnetic field, sort of perturbations. Perturbations in a magnetic field could be caused by currents. Currents are caused by moving charged particles. And so you guess that these moving auroral electrons are creating a current that's perturbing the magnetic field. And the intensity of that current is about 1 microamp per meter squared. And that's roughly consistent with current densities in Earth's aurora. Okay, that was the observational way to look at this. Here's the Dr. Seuss way, which I actually prefer. You have closed magnetic field lines in the center with no plasma on them that our instruments can measure. You have closed magnetic field lines outside of that, where their electrons are just kind of orbiting around the field lines. And then you have open magnetic field lines on either side, and we see auroral electrons right at the boundary between open and closed. I said we see 13,000, and each colored dot on here is where we see those 13,000 auroral electrons. The black traced regions are regions of very often closed magnetic field, and you can see that they're generally clustered around these closed magnetic field line regions, not inside, but there are auroral type electrons at other places on Mars too. And we see that these electron energy distributions have characteristics and occur at all. There's variability in their occurrence and in their characteristic. There's variability with Martian season as Mars rocks back and forth throughout the year. There's variability with the direction of the solar wind magnetic field, which may mean that they're closed or open field lines at some times and not others. And there's variability with solar wind pressure as these regions shrink and grow. This tells us that the solar wind is playing some role in auroral processes at Mars. It's either playing a role in whether or not electrons can access the atmosphere at all, or it's playing a role in the acceleration process that is forming these auroral electrons. And finally, this is in small print, but it's the coolest part to me, our highest energy events occur during solar storms. And as a matter of fact, the original UV detection I showed you a couple slides ago also occurred during a solar storm at Mars, so that appears to play a role there as well. What's causing these? We don't know, really. We have 4 ideas, and I think all are happening. And because we have 3 sets of observations, everybody has their favorite idea. And their observations, I agree, support one idea compared to the other options. And so really, I think all of these processes are happening at Mars. Some of the UV observations, especially the original one, supports an idea that low-energy electrons from the day side are transported around to the night side and funneled down into cusps, where they create aurora. These are low-energy aurora. And the line ratios that they get of different intensities suggest that it's a low-energy electron source Their subsequent 7 other observations suggest that they kind of now agree with our electron observations, that this is a more Earth-like situation where you form field-aligned potentials, and those field-aligned potentials accelerate particles down into the atmosphere and ions away. Also, magnetic reconnection. Mars is such a dynamic place with these crustal fields spinning around. You also have opening and closing of field lines, and I mentioned that that gives particles energy. That may give some particles enough energy to create auroral like signatures as well, or pointing flux and waves and things like that. And finally, some of our accelerated electrons are seen in the magnetotail current sheet at Mars as well. And the question to us is, even if the current sheet is what's doing the accelerating, we're observing them way down here at 400 kilometers. And so it's kind of surprising to us that the current sheet particles have access to such low altitudes. So there's interesting physics and interesting things to think about in all of these options. Finally, this is something that's been going on recently in the last few months for us. There are consequences that are interesting to me and to others of each of these 3 observations. Number 1, if we're seeing light in UV, at least in a UV spectrum from Aurora at Mars, can we take pictures of Aurora at Mars? Can we take pictures of them at UV wavelengths? Can we take pictures of them at visible wavelengths? This would suggest no, because it's all black. But on my screen, it suggests yes. But that's okay. You might see, it's not Aurora borealis or Aurora australis at Mars. It's Aurora messed up Alice or Aurora equatorialis or something like that. And so we're working out now with modeling calculations whether you could see something in the visible. We know that you can see something in the UV. And we're also talking with people from the Marcy team on MRO, which are taking observations in the visible, some of them at night side, to see if we can go look at their observations and detect visible aurora at Mars. Consequence number 2, electrons are moving down into the atmosphere. What are the consequences of that? They're adding energy to the atmosphere. They're probably colliding with particles in the atmosphere and ionizing them. And so we have some model calculations that suggest that the electron density in cusps of the night side atmosphere, electron density as a function of altitude, can actually be quite large in these magnetic field cusps. It can approach the day side electron density. And so you have little patchy night side ionospheres at Mars. Consequence number 3, if electrons are moving down and ions are moving up, how many ions are moving up? Is this an important atmospheric escape process? And this is something that we need to think about. I don't think anyone knows the answer. My personal feeling is that it's interesting and sexy, but maybe not that important, because the cusps are relatively small. But one thing to think about is, long ago in Mars's history, when the whole planet was covered in these crustal fields, you had cusps everywhere, and this has been a process that's been going on for a long time. So who knows how important this is. Finally, there's the next Mars Scout mission will be launched in 2013, and it's basically designed to address many of the issues that I talked about today for you. The PI is Bruce Jakosky at University of Colorado. It'll arrive in 2014, and it's called Maybin, which stands for Mars Atmospheric Volatile and Escape Mission. That's how they got the N. There are 8 science instruments that will measure the reservoirs for escape, the ionosphere, neutral atmosphere, the drivers, the photons and particles that are hitting the atmosphere, and the physical processes for escape. We'll take observations in the present epoch, and we'll take observations of their variability with the different drivers, and we'll try to piece together how important each of the 6 processes I described to you has been over solar system history. In addition, we'll be measuring isotope ratios in the upper atmosphere to try and figure out how important atmospheric loss has been over time as well. And this is everything I just said, so if you're just walking in now, you got here just in time. The Martian plasma environment can teach us about climate evolution, upper atmosphere, and space plasma physics. Woohoo! Not just at Mars, but at many other bodies in the solar system and in the universe. So it's a great place to go learn about all of these things. Crustal fields are really cool, and they create a complex field topology, and they're spinning around and opening and closing, and it's more similar to the sun than other planets. Atmosphere escapes from Mars in a lot of ways, and bulk escape is something I'm interested in right now. Auroral processes occur and are controlled in part by the solar wind, and Mars is just really neat. And I think it's neat, and now hopefully you do too. So thanks very much.
Well, have a little bit of time for questions, and I'll be happy to hand the microphone to you one at a time.
I would assume that there's not much room for currents in the Martian upper atmosphere. Is that true? I mean, there's not much of an area where you could have a lot of currents because there just aren't enough ionized particles.
That's a good question that I don't know the answer to specifically. But I know that the people at my lab, Matt Fillingham, who's doing this model, is also using our electron spectra, propagating them down into an atmosphere and figuring out where the currents are, how strong they are, where they flow. And he knows that there is a region near the main peak of the ionosphere where currents can flow, Hall and Peterson currents both. And he thinks that could be significant for the night side ionosphere. But it's no Earth, that's for sure.
Very nice talk. The Martian plasma environment is going to affect the potential habitability of Mars. And I wondered if people who, like the MEPEG or the Mars MSL landing site committee has taken that into account when narrowing their selection down to the final 3. And whether you know that, and if they haven't, they should know. So send them a white paper.
Yeah. Do you want me to respond? Yeah. I don't know. I don't know if no, I don't know if MEPEG or MSL has taken into account locations of crustal fields, things like that, when selecting a landing site. I know for the current set of rovers, when they were picking landing sites for that, I contributed maps of the crustal magnetic field, hoping that they would go to someplace interesting. But I understood that that was relatively low on the priority list compared to where it was safe to land and where water might have flowed and things like that. I know there's an active presence from our subset of the Mars community at MEPAG. People like Steve Booker and Paul Withers regularly go. And so I would assume that they're standing up and shouting and raising their hands. So.
When those portions of the atmosphere escape from Mars, do they just follow in the wake of the planet, or do they follow the stream of the solar wind?
Yes. Yes, the stream of the solar wind, I mean, the solar wind flow direction is like you would imagine in a stream. As you're coming in on the day side, it's sort of diverted around, and then it fills in on the night side and heads on downstream. And so I imagine these bloopy plasma bubbles, when they get torn off, are just sort of advected in the flow and kind of flow downstream.
Has any spacecraft tried to follow in the wake of Mars to detect this?
No, but New Horizons, Pluto Kuiper Express at Jupiter, traveled right down Jupiter's magnetotail, and they have very energetic particle signatures. I don't know how energetic, but they have energetic particle signatures that they believe are similar plasma bubbles in Jupiter's magnetosphere that are being advected downstream. And we also know at Earth, in Earth's magnetotail, this is where the term plasmoid originated. Flux rope is sort of, flux rope is to rectangle as plasmoid is to square. Plasmoid is a more specific term of flux rope. And plasmoids in Earth's magnetotail, the magnetic field lines in Earth's dipole get stretched out in the magnetotail, and it's believed they can get stretched out so far that they can pinch off here. And then you get this plasma bubble called a plasmoid that's being advected downstream. And those have been observed frequently by the fleet of space physics satellites. I don't know of any that are specifically following any downstream other than Pluto Kuiper Express. I have a question. So do I do anything else other than Mars that I would want to tell you about for 30 seconds? And actually, I want to ask for your help. So there's an EPO project that's being sponsored by DPS, and it's being run by Nick Schneider at University of Colorado and myself, and it's called Discoveries in Planetary Science, and it was Nick Schneider's idea. And it's basically trying to take recent advances in planetary science that have not yet appeared in college textbooks and develop little tidbits of curriculum that college instructors can use in their classrooms to stay current with planetary science. And it's a 4-slide format where we describe a recent discovery there's some press release or journal article on. We describe the underlying planetary science and physics processes that are responsible for that discovery. We discuss the big picture implications, and then we give you links where you can go search for more information. But there are only 2 of us doing this, and so the reason I'm mentioning this to you is because we're always open to ideas for topics, and we're even open to you making your own slide sets and contributing them. So if you have any ideas for something in your specific field that needs to go into textbooks, send me an email.
How do we get them to you?
Send me an email. How about send me an email with ideas or send me an email with slides. If you go to the DPS website, there's an email there, or you can send me an email as well, an education portion of the DPS website.
That's what, dbrain at berkeley.edu?
brain@ssl.berkeley.edu. SSL is Space Sciences Lab.
Any other questions? Okay, well, if not, David, thank you very much. It's exciting to hear. I was unaware of the recent arrival of Mars into the Aurora research, so that's cool. And
We
it's good that
finally
we've
made
got
it.
another
Couple of centuries
spacecraft heading
after
there
Earth.
soon, so thank you very much.
Okay, thanks.